Hello and welcome. In this video, we're going to take a look at functions and function notation, as well as domain and range of a function and how to construct the graph of a function. So let's get started. Now, a function f is just a rule that takes any element, some sort of object, x, in a set of objects, a, and assigns to it some unique element, f of x, in another set, b. And so here's a little bit of a diagram. We've got a collection of values here in red, which we've called the set A, and x is just one of many possible elements in that set. We could also name it anything else we like, and it would just be an arbitrary value somewhere in this collection. And when we put that into our function takes every value in A and gives us back a value of a different potential type, a number or a value in the set B. And when we have that output, we call it f of x, and that would be an element of this blue set, the set of values b. Now, these also have specific names. This red set here is called the domain. Now, the domain is the set of all values for which the function is defined. So the domain is anything that if you were to use as an input to this function f, that f could provide a meaningful output. Now, what is the set B? We call this the codomain. Now, the codomain is the set of all of the values for which f of x is constrained to. It basically tells us the potential values or the type of values that we might get from a function. But not necessarily every one of those values is going to be outputted. What we're usually more interested in knowing is the range of a function. The range of a function f is the set of all possible values of f of x. And this is only consisting of values that we do actually get outputted from the function. And so it is a subset of the codomain. Here's a quick example of a function where we can determine the domain, the codomain, and the range. Well, here we have a function f of x equals x squared plus 2. We can think about the input of this function as being just some value x. And then that is plugged into this function, and that function takes that value of x and squares it first, and by order of operations adds a value to it second. And this is the output. This is f of x. Now we can start to think about what kinds of values are able to be squared and then have 2 added to them. And if you think about all of the real numbers that we've looked at on the real number line, any one of those numbers can be squared, and of course, 2 can then be added onto it. So our input here could be out of any of the possible real numbers. And if we take a real number and we square it and we add 2, we know that we're always going to get something that is, again, a real number. So our notation would be f is a function that maps a real number to another real number. But upon closer inspection, if we take any value, whether it is on the positive part of the real number line or the negative part of the real number line, when we square it, we always get a value greater than or equal to 0. And we know that x squared is greater than or equal to 0, so that x squared plus 2 will always be greater than or equal to 2. And so we would say that the domain here is all real numbers. The codomain is also all real numbers. That only describes the type of number that we can get as output. In reality, our codomain is not always possible. The only possible values of f of x are values of x squared plus 2, which is greater than or equal to 2. So we could write that as an interval notation. Our range is simply the subset of real numbers from 2 inclusive to infinity, with infinity always using a round bracket. Now, thinking about this function notation a little bit more, we can always choose a different value and actually replace our x with a number that is any real number. So we can make this into a nice procedure where we pick various values that are real numbers and plug them in and construct the output. And that's what we call a table of values. Well, let's pick any real number as being our input for x. Of course, a nice easy number is to pick 0. Now, using function notation, we could write f of 0 so that you can see that 0 is our input and f of 0 is the output of this function. Now we have to compute that output by taking the value that is our input, squaring it, and adding 2. And then, of course, a quick calculation, we can find out that the output is the value 2. And we can try this for various different values of x, so long as we choose any value of x that's in the domain of our function. We could pick 10, for instance, and as long as we write our function notation out correctly, we'll see f of 10 is equal to 10 squared plus 2. And this gives us the output 102. Maybe we should try one negative value. Now, with a negative value, such as -5, it's important to include parentheses so that the negative is squared and then becomes a positive value and add to 2. Now, of course, we can't do this for every real number because there's infinitely many of them, but you can then construct at least enough information here to hopefully get an idea about domain, codomain, and range. Now, it's important to know that we don't always need to pick a specific value of a real number and plug it in. We may choose an arbitrary value. So what if we were to let a be a real number? If we ever see f of a, that just means that in our notation, a is our input, and we'll take the value a and square it and add 2. Or maybe my real number is the sum of a and h. What if I were to make my input something of the form a plus h? Well, in that case, that's still a real number and it still works as input. We have to include parentheses a plus h so that we can square the entire real number. A plus h is our input. We don't want to square a or just h. We want to square the result of adding a plus h together as being our input. And that means we'll have to FOIL this out. And our output can be written as a squared plus 2ah plus h squared plus 2. So essentially anything that you want to provide for input, whether it is a numerical value or it is some sort of symbol, the symbol, let's say even a happy face would do, will always just be our input to this function. So then happy face would represent a real number, happy face would be squared, and then we would add 2 to that. It's simply a placeholder. When we put x as our input, that means that x is representing anything in the set of the domain. Now, before we dive into the graph of a function, there is one other special type of function we should mention, and this is a piecewise defined function, or simply a piecewise function. And this is where you would like to have a more tailor-made function that will do different things to your input with the condition on what kind of input is provided. So for instance, you may find that your regular wage is $12 an hour, and you want to know that if you are inputting the number of hours, you can get the output as being your wage. And it would just simply be a quick multiplication of 12 times the number of hours. But if you were to work more than 8 hours in a day, let's suppose, and you got some sort of overtime, maybe you'd be earning something like $18 an hour for remaining hours afterwards. In which case, we would want our function to behave differently if you have a value that extends beyond 8 hours in a day. So we would want a function then that would multiply your number of hours by 12, but then additional hours would be multiplied by 18. That's kind of the idea behind a piecewise function. For a piecewise function, we can have different rules applied depending on the input x, but only one rule may apply at any single time. Additionally, for whatever x value we input, we only receive a single unique output f of x. Let's use our wage example as a way to construct a piecewise function. So we might use w instead of f for wage, and instead of x being our input, we might use t for the number of hours that we've worked. Now, supposing that we have a $12 per hour wage, our total wages could be computed by 12 times the number of hours worked. But let's suppose that we will earn overtime if you end up working more than 8 hours. Then we should make a condition on this that it will only be used when t is a value from 0 up to but not exceeding 8. Now, if we were to work more than 8 hours, then we know that we would already earn 8 hours of $12 an hour, which is $96 total. Remaining hours would then, let's say, earn our $18. So then we should take an additional 18 multiplied by how many hours are exceeding 8. which would then be t minus 8. So that if we have 1 additional hour and t is 9 hours, then we'll have $96 and we'll have 1 additional hour multiplied by $18 an hour. And we should only apply this rule if t is greater than 8. And now we can try out a table of values, keeping in mind that there are 2 rules with conditions on when to use each rule. But neither one of these conditions is used at the same time. The first rule is only used up to and including 8, and the second rule is only used for t exceeding 8. So, a table of values. T will be our input, and our wage, or total wages for that time, will be our output. And we could start off with a 4-hour shift. And if we only work 4 hours, then we'll only be using the top rule. Total wages for 4 hours. And that's simply calculated as 12 times 4, giving us $48 total wages. For an 8-hour shift, we'll only use the top rule, since t is up to or including 8 hours. And so we can see a total wages for 8 hours is $96. Now, if we were to work a 10-hour shift, now we're going to have to use the second rule, since now we have t exceeding 8. And we'll have a little bit more of a calculation to do here. 96 plus 18 times 10 minus 8, which is 2 hours. 2 hours of $18 an hour. Add to 96. And now we can see our total wages for the day would be 132 using the second rule. Okay, now that we have the idea of constructing a table of values, we can then also talk a little bit more about some functions that have gaps in their domain, where the domain is not all of the real numbers. And once we've got that idea, we can start thinking about graphing these functions. Since the domain of a function consists of all of the possible input values of a function, then we know that the domain must exclude all of the values for which f of x is undefined. And if we're given just a very basic operation such as division, then we know that we have restrictions on that where we cannot divide by 0. And so thinking about the function 1 over x minus 4, we might want to think about what values of x would cause us to end up dividing by 0 when trying to compute f of x. Well, we know that we can't divide by 0, so we could even write down a little restriction x minus 4 must not equal to 0. But it's better to rearrange that so that we can see that x may not equal 4. Just by treating it much like an equation where we have equal to 0, we can still solve for x when we have a does not equal to symbol. And we'll see that x cannot equal 4, and that is the only value where the denominator might be 0. So as an interval, we can have all of the values from negative infinity up to 4, and a second interval of values from 4 to infinity. And our domain would consist of all of the numbers in the left-hand interval or the right-hand interval, but excluding the value x equals 4. Another example would be when we think about the operation of square rooting some sort of value. We know that we can't square root a negative value, and for that matter, we can't take an even-powered root of a negative value for roots of 4 or 6 or 8. Any even-powered root. We have the restriction where we know that x must be greater than or equal to 0. And any one of these inequalities can then also be written as an interval. So in this case, our domain would be all of the values from 0 to infinity, but including 0. So any sort of combination of division or roots, we can start putting them together, and we'll find out that there may be several intervals or several values that must be excluded from the domain of the function. In certain cases, it's also best to try factoring. Here we have a function and we have a rational expression. Our rational expression, as we've seen before, it's okay to have 0 in the numerator so long as we don't have 0 in the denominator. So if we were to factor this, we could then rewrite our function h of t as being 2 times t minus 4. And we see that if t is equal to 4, we simply get 0 in the numerator, and that's not a problem. But by factoring the denominator, we see that having t equal to 4 or t equal to negative 2 will end up with a division operation dividing by 0. So a very quick restriction here, we can see that t minus 4 cannot equal 0, and we cannot have t plus 2 equal to 0, leaving us with t not being able to equal 4 and t not being able to equal -2. So the domain of this function consists of 3 intervals, breaking the number line up from -infinity to -2, an interval from -2 to +4, and a third interval from 4 to infinity. Now, it's very important to note that in rational expressions, we can cancel our t minus 4 and our t minus 4. But canceling these two things out will actually change the restriction on domain. So even though this is equivalent to 2 over t plus 2, the functions themselves are not entirely the same. It may be an equivalent function, but it's only equivalent for all of the values except for 4. This new function allows us to have any value of t except -2, whereas our original function will not allow a value of 4. This is an important distinction to make because we will see some particularly interesting behavior with functions that can be made equivalent to another function, but only with a difference in domain. Keep that in mind for now. It's always best to make sure of the domain of the original function before you start doing any algebraic manipulations. Okay, well now it's time to think about the graph of a function. We use the input and the output of a function to construct the graph. We talk about ordered pairs, typically with x and y being our two axes, where x is any value in the domain of f, and if we plug that value in and get the output f of x, then that is our y coordinate. Thinking about the function x squared minus 4, we can imagine that any real number should be allowed for input. And we know we're going to get another real number as our output. X will represent our input, and y will represent our output. And we can try various different values in a table of values. It might be worthwhile choosing some values close to 0 to see the behavior. So we may try values from -3 to +3 and going up by integers. Plugging each one of these in, we can find the output. We'll see there's actually quite a nice symmetry with this particular graph. And plotting each of these, we can use the coordinates. And once we've got the coordinates, it might be worthwhile to start thinking about what kind of scale to use for our x and y axes. And I've only chosen values from -3 to +3, so I'll try to make sure that my axes fit that information on there accurately. And I've got y values that range anywhere from -4 to +5, so I'll try to make sure that my y-axis is able to fit all of that information. And even if the scale of the y-axis and x-axis are different, we still get a good idea about the shape of this graph. Once we have all of our axes labeled with a scale, then we can put on all of the ordered pairs as points. Doing our best to draw a nice smooth line through these points, we can get a decent idea of what the shape of this graph must look like. Now, you'll notice that as we draw through the graph, we will never have 2 points directly above or below each other. Due to the fact that every x has a unique output, we have something called the vertical line test. The vertical line test says that if a vertical line does intersect the graph of a function, then it must only do so once. We may have occasions where a vertical line does not cross the graph, and that would be where that value of x is not in the domain. Let's see if we can graph a piecewise function. Here we have a function f of x that has 2 different rules. One of these rules is to take the value of the input x, square it, and subtract 4 from that. But we'll only apply that rule if x is less than or equal to 1. In our second rule, we'll be taking the value of x and we'll double that. We'll subtract the result from 1, but only do that if x is greater than 1. And this means that as we're constructing a table of values or as we're constructing ordered pairs on our graph, when we get to x equals 1 or x equals 1.001 on the other side of 1, we may find that our graph doesn't have a nice continuous line through it. We may see some sort of break in our function, and it may skip from one value to another. So let's see. our x squared minus 1 function, we already know how to graph that, but we are only going to use the graph of that function for values of x less than or equal to 1. So we can start off with that piece of our piecewise function. And here's the graph of x squared minus 4. Now we can continue this line as far as x equals 1. And since we can include that point in this piece of our function, we will indicate that with a solid dot, because we do know that when we plug in the value of 1, we'll end up with the value of -3. But we might want to try making a little table of values for the function 1 minus 2x. Well, let's pick a couple of values where x is greater than or equal to 1. We could plug in values of x equal 2, 3, and 4. And we should get f of x, or our y coordinates, as -3, -5, and -7. And we can start plotting those on there, although it looks like -7 is starting to get off my graph a little bit. Now it does start to look like these are forming a straight line. And it is worthwhile to see whether or not that straight line is going to connect to our previous part of the function. What we could do, even though it's not included, we could start to plug 1 into this function. And that will give us 1 minus 2 times 1, or simply -1. Now this point does not exist on the graph necessarily, but it's still worthwhile to see where it should be, 1 and -1. We could then see that that's still on the same path as this function. It still all forms a straight line. But since it's not included in our graph, we should indicate that with a round circle. And then, forming a nice straight line here, we can see that our function comes from that open circle without including it. It doesn't end up shading that dot in. And so we've got this small little disconnection between the two pieces of our function. And that is totally okay. The pieces of a piecewise function don't all have to end up connecting with each other. And that's how we can find that we get these small little jumps from one value to another. But it still passes the vertical line test because we say that the solid dot is included, but the hollow dot is not. And a vertical line would only pass through the solid dot and not pass through a second point. And there we go. We got a pretty good idea about what kinds of functions we're going to be looking at. Most of our functions should end up being f of x equals a single rule, but piecewise functions kind of provide us a very unique glimpse into some very customizable functions where if you wanted to have a calculation be done differently with a conditional on input, then a piecewise function is going to be the only thing you can really think about. Now, graphing is going to be very important throughout this course, and we'll look at many common functions and have a good idea about what kind of graphs they're going to have. That way, instead of having to always rely on a table of values, we already know the basic shape, and then we can just apply a few little shifts or stretches to be able to come up with a shape of a brand new function that has a very similar type. We'll keep that for a future video. Thanks for watching. I'll see you again later.